Okay, so I did this problem, but I'm going to do it again. I'm going to do it this time using the more circuit-based model where we could actually draw this like this. I'm going to actually put two resistors, even though we'll see that doesn't truly matter. And this is R1 and this is R2. So in this case, this whole wire has some resistance that I can calculate. And then this tiny wire has a resistance that I can calculate. And then I can treat this as a normal circuit problem and use the loop and the junction rule again. Okay, so let's start with finding these resistors. So remember that resistance is rho L over A. So if I have a wire, the longer it is, the higher the resistance, and the bigger the cross-sectional area, the lower resistance, where the resistivity is a property of the material. So in this case, it's copper, which I looked it up, has a resistivity of 1.68 times 10 to the negative 8th ohm meters. So let's I'm not going to calculate it, but I have the same wire I had before. The thick wire has a diameter of 0.4 millimeters, and the thin wire is 0.01 millimeters. The length of this wire is 0.4, and the length of the short wire is 0.01 meters. So R1 is going to be equal to rho L1 over A1, and R2 is going to be equal to rho L2 over A2. And I just went ahead and calculated these two things for you. You could plug them in. R1, just so you can see, is 0.053 ohms. That's really small. R2 is equal to 2.139 ohm, which is really large. I mean, really small for a resistor of a wire, but it still works for this particular problem. But you see here, one of the things I'll do at the end is to redo the problem and assume that the wire has no resistance. And you can imagine if this was a 200 ohm resistor, then that would be essentially negligible. Okay, but that's an important thing to talk about. Wires do have resistance, but a lot of times we pretend like they don't. Okay, so now I can do my loop rule again. I can start right here, and I can go around the loop. And if the loop rule says delta V equals 0. So if I go across here, I go across a battery, I have an EMF of EMF, which is 1.5 volts in this case. It's a 1.5 volt battery. And then I have this, I'll call this I1, I'll call that I2 for now. So this is going to be the change in voltage over that resistor is going to be EMF minus I1 R1 minus I2 R2 equals 0. And I'll get back over there. Now here I have a junction, and I have a current coming in, current leaving, such that I1 is equal to I2, which, yeah, duh, okay, but I'm trying to be fair here, people. I'm trying to be fair. So that means that this could be written as EMF minus I1 R1 plus R2 equals 0. Now I can solve this for I1, and I get I1 equals EMF over R1 plus R2. And I get 0.68 amps. Now, if you look at the previous problem, I did this and I got 0.7 amps. And the difference is that before I had electron mobility and charge carrier density, and it wasn't exactly the same as this. Okay, so it's just slightly different values, but close to the same answer. Okay, let's do this one more time. What if I assume this is equal to 0? Then I would just have this. Let's see if I can do it one. EMF minus IR2 equals 0. So I would be EMF over R2. In that case, I didn't put the numbers in, but you can do it. I just divide by this. So it'd be still pretty close to the same value. So which is better? Is it better to do this method or that method? It depends, right? It depends what you're trying to do. I still like this method. It seems like it's a lot more work, but you really get a better feeling for the electric field side of electric circuits, which I think is important in a lot of cases. Okay, I'll stop there. Now we're going to do some more later that are more complicated than this, but I'll see you guys later.